everyone. This playlist of videos is meant to take you through pages 26 and 27 in our packet so that we can start pursuing definite integrals with u-subs. That's kind of a natural combination of the two things that we were doing most recently while we were still meeting in person, because we did talk about the idea of definite integrals. Definite integrals are the ones that involve plugging in the two endpoints and subtracting, as opposed to the indefinite integrals, which have the plus c at the end. So that's basically what we kind of left off doing. And the natural progression from there is to do problems like that that require a u-sub, problems that wouldn't necessarily just work with a traditional power rule or a memorized antiderivative. So the goal on page 26 is to just familiarize ourselves with the topic, and then on page 27 and 28 begins the actual independent practice. With all of these videos that you'll see throughout the next few weeks, the goal is basically to just kind of get the idea and get the hang of things, almost as if we were doing an in-class lecture. But unlike the in-class lecture, you do have the total luxury here of fast forwarding or rewinding, and of course, completely skipping over certain things if you feel like you already get it and you just want to move on to the independent practice. All of the answer keys are posted on my website, so in theory, if you just want to watch part of a video or just certain segments and then stop early, you are not obligated to watch the entire thing. So feel free, of course, to kind of watch as much as you need in order to get the hang of things, but certainly don't feel obligated to hang through all the way, especially if this stuff makes sense to you. Likewise, if you're working through something and you have a question, please don't hesitate to email me, because my email address has been posted on my website and Google Classroom. Hopefully it's easy to find, but I definitely want to keep those lines of communication open, especially because learning calculus through videos is not necessarily the most intuitive way of doing it, but I think we can make it work. Just make sure that you communicate clearly if there's something that doesn't make sense, and I'll do my best to clarify in either a future video or an email response, whatever's easiest for the nature of the question. So we'll start on page 26 in our packet, and we'll start specifically with question number 12. The deal with this question, probably obviously, is that it's a product rule with a chain embedded, so naturally it seems impossible to do the antiderivative in order to plug in the pi over 4 and the 0 and subtract. So this, by all accounts, must be a u-sub problem. Now, we know enough about u-subs to kind of know how to pick our u, and since we have a product rule, that definitely kind of implies that one of the elements of the product is going to be our u, hoping that the derivative of it is going to be our du. And by strategic picking, I can kind of tell that choosing tan for my u-sub is going to be a good idea, because the derivative of tan is secant squared, and that certainly seems like it'll take care of all the substitutions. So I'm just going to kind of do my normal thing, which means I'm going to take my workspace and just kind of subdivide it into two areas. I'll use the space on the left as my u-sub and the space on the right as my actual substitutions. So I'll begin with the u-sub, let u equal, and again, as discussed, we're going to pick tan x because its derivative is already part of the problem. And then, just give myself a little bit of a boundary here, I'll start making my initial substitution. Initially, the tan is going to be replaced with the letter u, but I still have the secant squared x dx to replace. And as you know, I like to make my first substitution in terms of u and then do a separate substitution for the dx part. But if you want to do this all in one step because you're good enough at u-subs now that you don't need to do those interim steps, that's fine too. Now, going back to my side work then, du is, of course, secant squared x dx. That is a clean substitution for the secant squared x dx that I have in my main integral. So the integral of u then replaces with du, and now it looks like we're good to go. Now it looks like I have an integral in terms of u that I can definitely do. The thing that I haven't really paid much attention to yet, though, is the 0 and the pi over 4. Those were technically part of the original problem, but you'll notice I did not write them here, and I didn't write them for a very important reason. Those two numbers, 0 and pi over 4, are x coordinates, But if my integral is in terms of u, then those x coordinates are not compatible with the variable that I'm actually using. If I'm using the letter u, then the only compatible coordinates are u coordinates. So this is where we actually have to now pay closer attention than we may have used to about the nature of converting the problem from x to u. If I'm converting all of the variables x in the problem, that includes the x coordinates that we're using as the limits of our integral. So in part B, that's kind of what this is alluding to, where it says use your u sub to rewrite the limits of the integral so they correspond to u values, not x values. That's basically a conversion that we're going to need to do. It's kind of like when you realize you're working on a science problem that was measuring everything in feet, and then all of a sudden the problem switches to inches and you're like, oh crap, I have to convert all of my numbers. Kind of the same thing. So the first thing I'm going to do as part of my side work, so you'll notice I'm still on the left hand side here, is I'm just going to write the two original x coordinates that I had, x equals 0 and x equals pi over 4. Now, this is just my own personal style, so you don't have to exactly mimic my structure here, but what I'm trying to do is show the conversion from x coordinates to u coordinates. So I'll start with x equals 0. Now, if you're wondering how in the world I'm supposed to convert that, take what we know about u. This is the only fact that we currently have about u, which is the letter that I want to convert the problem into. The only fact that I know about u is that u equals tan x. So logically, if x is 0, then the u coordinate must be found by doing tan 0. In other words, to convert the coordinate, simply plug the original x coordinate into your side work equation. So in this case, I'll plug in 0 into my into my side work u equals tan x equation, and then I'll just evaluate that. Tan 0 is sine 0 over cos 0, so that's 0 over 1, which is 0. Now, don't get too ahead of yourself. It's very uncommon that the u coordinate and the x coordinate are actually the same, but sometimes it happens. This is an example of such. Now, let's do the other conversion and just make sure that we understand what exactly is going on. To convert the other original x coordinate, pi over 4, I again will go back to my side work. My u equals tan x. So to convert pi over 4, I'll call this u equals tan pi over 4. And then I have to do a quick conversion here too. Tan of pi over 4 is sine pi over 4 over cos pi over 4. Sine pi over 4 is root 2 over 2. Cos pi over 4 is also root 2 over 2. So this is kind of a nice tangent. It would be 1. Now notice what I've done. Now instead of the integral going from 0 to pi over 4, I've basically made an integral that now goes from 0 to 1. And that's kind of the important thing. Important enough that I'm actually just going to highlight it for emphasis there, because the purpose of converting is to give myself now an integral with relevant limits, limits that are actually useful for the problem that I'm trying to solve. So going back to the big picture then, just to remind us of where we've gone and where we've been, we originally u sub to turn the actual structure of the antiderivative in terms of u, and now one step further, I'm going to add the limits back into the problem, just so that way I don't ignore them. So I have the new integral from 0 to 1 with its new u coordinates, and then I have the u du in terms of u that I found from my first step. So now that I have a problem that is entirely in terms of u, it's got u coordinates, it's got u variables, it's got an implicit du, now I can do the antiderivative because it's totally consistent. Just like with all calculus problems, you can only work with these things if all the variables are consistent. If even one mismatch occurs, the calculus falls apart. So now we can do our traditional antiderivative steps. U is just going to be a power rule because it's technically u to the power of 1. So if I do my power rule and add 1 with the coefficient, it becomes 1/2 u squared. Remember, with these problems, definite integrals, you don't need to put the plus c because it's just going to cancel out when you do your subtraction anyway. So in lieu of the plus c, we do our evaluation bar, and we say we'll evaluate at 1 and at 0. Technically, when you read it, you do say from 0 to 1, but because when we evaluate, we plug in 1 first, then we plug in 0, then we subtract. I personally read it as 1 and 0 to remind myself of the order that I'm going to do the math. So now that I've finished this up, I have 1/2 times 1 squared, which is 1/2, minus 1/2 times 0 squared, which is 0. You'll notice you don't actually have to show all of the plugging in, although if it was a more complicated calculation, you might want to show it just to keep your work straight. It's not like it really matters, but you can definitely take some liberties if it's a nice problem like this. So once we subtract, which obviously is trivial, we get an answer of 1/2. Now, as you probably recall, that 1/2 is the area underneath the curve if I had graphed this crazy looking thing from 0 to pi over 4. Now, obviously, this would not be geometrically possible to graph and find the area of, so you can see why calculus was needed and why a u-sub was needed. This was a pretty messy problem. But the good news is now that we have such strong antiderivative techniques, we can make this happen. Now, in question letter D, because you'll notice I've kind of been doing questions A through C without really specifying. In question letter D, it says, show how to evaluate the integral in terms of x instead. And you might be looking at this going, wait, what? In terms of x? What we mean here is that if you didn't want to take this side work step of converting your original x coordinates to u coordinates, you do have another option. The second option is basically to temporarily do the antiderivative in terms of u just with no limits attached. Replace your antiderivative back in terms of x at the end, and then evaluate with the original x coordinates. Let me show you what that means. If I just pick up at the last step that I could do with the u sub, that was the integral of u du. Notice I'm not going to use the u coordinates because I want to demonstrate here why you don't actually have to go through this step. If you didn't want to do this side work step and convert the coordinates, simply take your antiderivative in terms of u and just don't write any limits on the integral symbol. If you do the integral 1/2 u squared, then notation-wise you're being a little bit casual here, but it's actually okay to say, well, if the original u was tan x, I'll make a quick replacement substitution. In other words, I'll go back into my original side work from the very top. I'll replace the u back in, kind of like we do at the end of a normal u sub problem anyway, and then I'll evaluate that in terms of pi over 4 and 0, the original x coordinates, which we know is fine because if this problem is back in terms of x, x coordinates are compatible. Now, of course, we have a slightly more complicated evaluation to do, and this would look like 1/2 times tan of pi over 4 quantity squared minus 1/2 times tan of 0 quantity squared. But it's definitely doable. In fact, it's the same math we did on the side work anyway. We know that tan of pi over 4 is 1, and we know that tan of 0 is 0. And of course, if you clean that up, 1/2 minus 1/2 times 0 is still going to give you the same answer of 1/2. Now, just in case you think one method is maybe better than the other, it's pretty obvious that they're the exact same thing. The conversion that you did here requires doing tan of pi over 4 and tan of 0, and plugging it in the x coordinate version of things still requires you to do the same math. So lest you think that one way will help you avoid complicated calculations, that's just not true. Unfortunately, you end up having to do the calculations anyway. But the upside is that if you feel as though the organization of just converting everything to coordinates of u is easier, then you never actually have to go back and write the letter x ever again. It's almost like you ignore the original x coordinates from that point forward. If you don't mind switching back and forth, it's okay to basically use the u sub as a temporary or a stopgap measure. Just quickly do a u sub, convert it back in terms of x once you got an answer, and then plug in your original x coordinates to your x version of the answer. And again, it totally works. It's just a matter of which way makes sense to you. So in short, in letter E, it does not matter whether you evaluate in terms of X or U. You'll get the same answer either way. You just have to make sure that you pick the method that is most consistent for you. Down there at the bottom of this page, you'll see a note about notation, and that, of course, is kind of meant to help you sort of summarize the two methods. Either change the entire problem in terms of U, including the limits, and remember in this context, the word limit refers to the numbers at the bottom and the top of the integral symbol, or the endpoints of your integral. And method number 2 is temporarily changing the problem in terms of U, immediately changing it back in terms of X, and then plugging in the original limits from the original problem. So again, one method may be better for you than the other, and that's fine. It is definitely a personal choice. So you might want to try both ways when you get to the problems on page 27 to see which way suits you better. I'm going to give you some time to just kind of process all of this before I do a separate video on page 27 with some examples. But as you probably know, the goal is basically to kind of digest this, and then on page 27 to do a little bit of practice. So take some time, make sure the idea makes sense, maybe even try a problem on page 27 just to see if you can do one independently. And then if needed, you can dip back into the playlist and choose some of the other examples from page 27 specifically if you want to see a more walked through or step-by-step example.